So for Lab 1, we're going to use something called HDL, or Hardware Description Language, to implement the three basic logic gates, AND, OR, and NOT, using only NAND gates. To start, we open the web development environment for the NAND2Tetris hardware simulator. The link to that is in the description. There are four sections on this page: the header, the hardware description language implementation, chip inputs and outputs, and the testing section. In the HDL implementation section, you can select which project you're working on and which chip in that project you're currently implementing. There's also a switch that will toggle the built-in implementation for this particular chip. Then there's the text editor where you can write your own implementation and hardware description language. Let's talk about the structure of our HDL code in the text editor. Below the file name is a description of the intended behavior of this particular chip. In the chip section is where your implementation will go. You have the keyword chip, which is declaring a new chip object called NOT, and within the brackets is where we have our input, output, and parts sections. The in keyword declares the names of Boolean input variables separated by a comma. We can think of these input variables as arguments or parameters of a function in general programming language. The out keyword declares Boolean output variables, which perform a similar function to returning values from a traditional function. Under the parts keyword is where we define our logic gates to perform Boolean operations on the input variables and send the resulting value to the output variables. The middle section is the chip input and output section, where you can manually toggle the chip's inputs and press the evaluate button to determine the output of your current implementation. The section on the right is the testing section, which contains the area for writing scripts to test your implementation and compare results with a known benchmark. A compare file contains the expected inputs and outputs, and an output file contains your actual inputs and outputs that are printed when you run the test. A difference table is generated that highlights the comparison between the compare file and your actual output file, with the incorrect actual output highlighted in red and the expected correct output highlighted in green. Now that you know about the user interface, let's go through and implement the NOT gate with NAND gates. The behavior of a NOT gate is that if the input is 0, the output will be 1, and if the input is 1, the output will be 0. So in order to achieve the behavior of a NOT gate, we just need to plug our single Boolean input into both of the NAND gate inputs. So the first thing we need to do is declare a NAND gate under the parts section. This NAND gate has two inputs, A and B, and one output called out. So I'll write A equals in, B equals in to connect the single chip input to both inputs of the NAND gate, and I'll write out equals out to connect the output of the NAND gate to the output variable or the return value of the chip. I'll end that line with a semicolon and go to run my test script, where there are three options: step, which allows you to step through the test script one comparison at a time; run, which will run the entire test script; and reset, which will reset the program counter back to the beginning of the test script. I'm going to hit run and to test my implementation, and it seems like it successfully passed the test. Now we're going to move on to the AND chip. So I go to this selector here and select AND. Now I should have the testing script and the starting HDL code for the AND gate. If you don't, consider using an incognito browser. The expected behavior of an AND gate is that when both inputs are 1, the output should be 1. Otherwise, the output should be 0. So how do we build an AND gate with NAND gates? Well, NAND gates refer to not AND gates. So when we negate the output of an AND, we end up with NAND. But the trick is, if we negate the output of NAND again, we end up back with AND. So we pass both our inputs into a NAND gate. Then we pass its output into a NOT gate, which we just built a NOT gate with NAND gates, so we can use similar implementation here. So I'm going to declare my first NAND gate and write A equals A, for the chip input A being fed into the NAND gate input A, B equals B for both of my inputs, and for the output I'm going to declare an output variable called NAND1. I'm then going to pass that output variable to another NAND gate to invert its output. So we declare another NAND gate with A equals NAND1, B equals NAND1, and out is equal to the chip output. So out equals out. We then test it, and it ends up passing the test. Finally, we're going to implement the OR with NAND gates. The behavior of OR is this one or that one. So if either input is 1, or both, the output will be 1. So how can we replicate this behavior with NAND gates? Well, the output of the NAND gate will always be 1 unless it has two 1s as its inputs. So we can utilize this by feeding both of our inputs into a NOT gate made from ANDs, then feeding both of those outputs into a final NAND gate. The result is that when both inputs are 0, the output is 0, but for every other combination, the output is 1. So we declare 3 NAND gates. The first 2 are going to be used as NOT gates, so I'm going to feed one input into both inputs of the first NAND, and then the other input into both inputs of the second NAND. The last one will receive the output variables from those 2 NOT gates and send the result to the final chip output for OR. In future videos, we'll be building much more complicated circuits using AND, OR, and NOT gates, which you can pretend are made from the NAND gate implementations that you just wrote. This concept of packing the complex NAND circuits into simple packages exemplifies one of the 8 great ideas of computer architecture, which is abstraction. Abstraction means that we can simplify and modularize complex systems by breaking them down into their component parts.